Hello and welcome. I'm your host, Allan Jude. Whether you're joining us live or watching this on a recording, thank you for spending your day with us. For those who are new to Clara, we're a team of open source experts specializing in ZFS and FreeBSD, helping companies across the world optimize systems and tackle complex technical challenges. So whether you're looking to build new or re-architect your existing storage pool, get support for or squeeze more performance out of ZFS or FreeBSD, or if you want to develop a new feature, definitely get in touch. Before we dive in today, I just want to make a quick note that we're currently running a limited time promotion on our ZFS support subscription. You can save up to 35% off your first year by signing up before February 17th. It's a great opportunity to start the year with direct access to expert ZFS engineers. We'll share more details on that later with a QR code. Now on to today's webinar. A new year, a new ZFS. We're talking about the recent release of ZFS 2.4 and what that brings to the table. We'll take a focused look at some of the most impactful changes and especially things you'll want to be aware of. So not just what's new, but what it actually means for your day-to-day operations. So we'll talk about some of the new capabilities and the performance improvements, some operational updates you should be aware of, and how to decide when it's time to upgrade. As we go, please post your questions using the Zoom Q&A system. We'll be monitoring that throughout and answering questions with the dedicated time at the end as well. Joining me today is Paul Dagnelie, Principal ZFS Engineer here at Clara and a longtime OpenZFS contributor. Paul,
Hi,
I'll
Alan.
hand it over to you to do your introduction.
Yeah. So I've been working on ZFS for a little over a decade now, in various parts of the stack. Lots of stuff in send and receive, lots of stuff on the performance side. It's nice to be here.
Thank you for joining us.
hmm
So yeah, we'll start right off the top by talking about some of the new capabilities that are in ZFS 2.4 that people will be most interested in. And the first one I'm really happy to be able to share with people. And this is the RAID Z sit-out feature. So if you have a pool with one or more RAID Z VDEVs, as a lot of people do, you may have noticed that sometimes one failing disk can make the whole pool slow. So I've seen systems even with like 7 different VDEVs of many disks each, and one single disk makes the entire pool slow. Because reads and writes are distributed across all the VDEVs, but an individual record of a single file is only ever on one VDEV. And then on that VDEV, it's split across all the disks that make up that VDEV. And so if one of those disks is very slow to read or write, it can mean that the system is stuck waiting for that one slow disk to finally answer or time out and give an error before it can return that chunk of the file. And, even if it's only 1 in 7 reads that are slow, you're usually doing more than one read at a time, and very quickly it just makes the entire system feel slow. So you might wonder, it's like, so with RAID Z, we have 1 or 2 or even 3 parity blocks, and we have enough to make up the data that was missing. So why are we waiting for this one slow disk if we already have enough information to go on without it? But by default, ZFS doesn't read the extra parity blocks because we want to save the bandwidth and the IOPS on those disks for the next read, because reads are distributed across all the disks, and because of the dynamic block size in ZFS, it means that we won't use every disk for every read. And so by avoiding reading the parity that we're most of the time not going to use, we have more performance for other reads.
Yeah. So the new feature that we came up with is what we're calling RAID Z sit out. And the basic idea is that as these reads come in for the RAID Z devices, we monitor the latency and the response time of each disk in the VDEV. Um, And then if one of the disks in the RAID ZVDEV is consistently slower than the others, is a big performance outlier, then we place it in the sit out state, um, where it doesn't respond to any read requests. Writes still happen so that your data still has all of the parity that you expect it to have, but we don't use it for reads. Instead, we read from the parity stripes and then reconstruct the data um, using the normal RAID Z algorithms. Um, if something temporary is going on with the disk, this gives it some time to catch up to whatever's going on, gives it time to get over whatever sort of performance hiccup is happening. Um, But if this ends up being a long-term state, if the device sits out repeatedly, and it continues to underperform, then the fault management system can determine that there's something wrong with the device and then replace it with a spare. And this allows you to get significantly better performance in these cases where you have one disk that's either temporarily or permanently becoming flaky.
Yeah, and so in those cases, we'll just use the parity to do the reads and keep the system moving quickly instead of being stuck waiting for that one slow disk.
Yep.
Uh, but what happens if we don't have enough parity, right? If we have multiple failed disks and this is happening,
Yes. So if you have a failed disk and things are in sit out, then we will still use disks in sit out. They are sort
just
of
only as a last resort kind of thing.
right. They are deprioritized, but if they're what we have, they're what we have, and we will get the data back one way or another.
That's great. I think that'll be a big improvement, especially for very large deployments. Like I know there was a lot of interest in this from some of the government labs who have huge pools with many disks and are like, yeah, this happens to us all the time. We really would love to have this.
Yeah.
So moving on to the next feature, start with just a little quote with a reminder. Every program and every privileged user on a system should operate using the least amount of privilege necessary to complete the job. And so with that, we have the ZFS allow system. This allows you to delegate privilege operations. So instead of having to use sudo or run as root, you can use ZFS allow to allow an unprivileged user, whether that's a regular user like a person or a kind of a service account like a backup user that just runs some automation, to allow them to do certain operations like create snapshots so that you don't have to reroute to add snapshots, or specifically replication, right? If you're doing automatic replication with something like Sanoid, you can set it up to run as a non-root user so that it doesn't have any permissions on your system. And we had a case where, backups, we want them to be performed by an unprivileged user. But there are two different kinds of backups in ZFS now. You can do a regular ZFS send, which will decrypt data and send it to the other system where it can then be received. Or you have a raw send, which allows you to send the encrypted version without the encryption key. So the remote backup site never has the ability to read the backup data, unless you, outside of ZFS, give them the key to be able to mount that data. And so when you're automating this, you might actually want to ensure that the backup user only ever has access to the encrypted copy of the data. This can, first of all, avoid accidental leaks, right? If you do a ZFS send and forget the raw flag, it'll say, hey, you don't have access to the plain text, only the encrypted data. And it ensures that even if somehow, the not password protected SSH key that you're using to allow your machines to SSH into each other, if that got compromised somehow, they would only have access to encrypted data that is useless. They wouldn't be able to get an unencrypted copy of the snapshot of your pool. And so this adds a new delegation where you can do the send raw permission, and that will allow only encrypted data to be replicated, and it won't allow unencrypted data to be replicated. So the existing send permission will allow either, but this new specific permission will only allow encrypted data to be replicated.
So let's take a brief diversion and talk a little bit about some ZFS fundamentals. Um, ZFS is a copy on write file system. And what that means is that when you have written your data to ZFS, once it's in place, you never modify that data. You can only replace it with a new copy written elsewhere. So anytime you go and update the data in a file, you're actually writing a new copy of that data to a different location and then updating the references that point to that data to point to the new location.
Right, and that's so that if the power goes out in the middle of you writing that new version, in a traditional overwriting file system, you don't have either copy. You have half
Yeah.
of the new one and half of the old one, and your file is hosed. But
Yes,
with copy on write, we put the new one over here. If the power goes out before we're finished doing that and updating the metadata, we still have the old copy. Or if it completes, we have the new copy. And we're always
that's right.
either A or B, never pudding.
Yep. And then this also enables some core ZFS features like snapshots and clones being so transparent and easy to use because we're always writing the data to new location anyway, so we just have to keep the old data around for a snapshot. Um, Another core property of ZFS is the idea of the pooled storage, right? ZFS is, I mean, it can be run on a single disk, but usually it's run on collections of disks. And you can add storage to it over time. But one thing that does happen in that case is that as you add new VDEVs to your pool, they're added empty. And so you can end up with these very unbalanced VDEVs. You know, you can have one VDEV that's almost completely full and another one that's almost completely empty, even if it's made with newer and better disks, where you'd really like more of your data to be on those newer, faster devices. And this can cause uneven performance and imbalances sometimes. um, Rewriting your data to take advantage of things like new compression algorithms or to use a new record size to take better advantage of RAID v expansion or other things like that had previously been a manual process. You had to, take the file, move it to a new data set with this new property set up, and do all of that sort of by hand or hack together a script yourself to do it, which was not a great state of affairs for users.
Yeah. And so with ZFS 2.4, we've introduced the ZFS rewrite command. So this is a new mechanism where you can specify a specific file or with the -r flag for recursive, directory, and ZFS will go through there and mark each of those files or the content of them as dirty, which causes ZFS to basically act as if you had overwritten the file with a copy of itself. So it will rewrite all the data with the new settings. So if you've changed the compression, it will recompress it with the different compressor and write that new copy. Or if you've used RAID Z expansion, you can now take advantage of the wider stripe size and get more efficient storage. And it basically rewrites all this in place, but without you having to manually, copy the files to a different directory and then copy them back, or any of the other tasks. And it's much safer to do with data kind of in place, right? You're not having to make sure you copied everything to the new place and that it's all up to date and so on. It lets you just do it all in place without the extra rigmarole. So it's basically the same as copying the file to a different directory and then deleting the original, but it all happens in place and avoids, breaking applications that expect the file to be in the original place. It does have the downside that this will grow your snapshots, right? All this data is actually changed. We're rewriting it. And so your snapshots will get bigger. And so if you don't have a lot of space, you might not be able to keep your snapshots when you're doing this. But there's a second version of this that tries to ameliorate not so much the snapshots part of it, but the fact that when you grow the snapshot, obviously, if you're using replication, that's going to cause a problem, right? So if you rewrite 100 terabytes of data and you're replicating to a backup, you might not actually want to have to resend 100 terabytes of data. So the rewrite command has the capital P flag, which uses a physical rewrite. So when you write data to ZFS, we keep track of which transaction group it was created in. With this -p flag, we'll say the content of this file hasn't changed since it was originally written, but the physical copy on disk has changed. And ZFS can use that to say, okay, so the snapshot is bigger here, but I know I don't need to resend this to the other side because the file contains the same information. It's just been compressed differently. And if I don't want to, get the same compression savings on the backup, I don't need to re-replicate it. One downside to ZFS rewrite, whether or not you use the physical flag, is that you can't change the record size of a file with it. Because every record in a file has to be the same size, the kind of record size of the file is set when you create the file. Because the rewrite command is just marking all the content of the file as dirty, it's not creating a new file, and so the record size can't be changed. But pretty much every other property can. So you can change the checksum algorithm. If you want to move from Fletcher 4 to SHA-256 because your CPU can accelerate that, you can do that. You can use newer compression. Like if you want to switch from not compressed to using LZ4, or you want to even go up to Z standard, you can do that. You can enable or disable dedupe and reapply it to all the existing data. Or even, undo if you in the past thought it was a good idea to set copies equals 3 on some important files, and now you'd like to get that space back, you can lower the copies and use the rewrite command to apply the new setting. One other caveat, this will undo any block cloning you've done. So when you use block cloning or ref links to make a copy of a file that uses the same data. If you rewrite one of the copies, that will become its own new copy because we're rewriting the data as if it was separate. And so that will break any of the cloning you did. So it will cause those files to suddenly seem to get bigger. So be careful with that. But on the upside, this can also help defragment your pool. If you, for example, as Paul was talking about in the previous slide, if you had a pool with a bunch of disks and then you added another set of disks that are now mostly empty, one of the main things you'd use rewrite for is to rewrite a lot of that data so that half of it would end up on the more empty disk to balance things out. Because you have a bunch of free space now, when you rewrite files that were written when you didn't have a lot of space and they were broken up across a lot of different places, rewrite will try to group those files back contiguously, and so you will have better read performance for them after. And it can also get rid of gang blocks, which we'll talk about more when we get to the improvements to the gang blocks themselves in a later slide. So yeah, the rewrite command is a very nice win and provides a lot of flexibility to kind of apply new settings and rebalance a pool without having to do a bunch of manual send receives or manually copying files around. As I mentioned in the intro, we've seen the response to our year-end promotion be very clear. Organizations are really serious about owning their infrastructure and controlling their storage. And that's why we've decided to extend our 35% discount offer on ZFS support packages until February 17th. A ZFS support subscription ensures you always have access to expertise to plan, deploy, and maintain your storage systems. Whether you just have a question about best practices or you want to double check a command before you commit to it, or you need help with a very specific workload, or you're dealing with a complicated emergency, having the Clara team to back you up will allow you to move forward with confidence. So if you're interested, definitely check out the QR code and visit our website. And if you sign up before February 17th, you can qualify for a series of discounts. Now let's talk about some of the performance enhancements that were added as part of ZFS 2.4. We'll go into detail in each of these, but I'll start with kind of a quick intro. The first is the unified allocation throttle. This controls how ZFS distributes data across multiple VDEVs. So we've done a lot of work here on, you add a new VDEV that's mostly empty and you want to rebalance some of the data on it because it won't perform as nicely. Or, when you're reading, you can only read from where you wrote those files to. Whereas if you add more disks, if you rebalance the data, now you can read from more disks and you'll get more performance. So the unified allocation throttle deals with how we distribute new writes across the existing VDEVs. Then we have gang block improvements, which Paul will talk about. Basically, when there's not enough, when the bits of free space in your pool are not big enough to write the whole block at once, we have to group a couple of blocks together to be able to write out the file. And there's a bunch of improvements to how that works. For encryption, ZFS now supports the AVX2 vectorized AES instruction, which, if your CPU supports it, can make encryption 50 to 80% faster on your CPU, which can be a really big win when you're dealing with large storage systems. And then lastly, we have the special device. So ZFS added the special allocation class device a number of years ago that allows you to put metadata and even small blocks on a file. But this has led to a tension where people are trying to decide how to make use of it and often are taking a single set of disks and partitioning them to try to have a slog and a special device on the same physical device. And that is definitely worse and it causes competition. Whereas with this feature, if you have a special device and don't have a separate log device, we will just put the ZIL on the special device and you don't have to do a bunch of, under the hood stuff to try to trick ZFS into doing what you want. So let's move on to the allocation throttle.
Yeah. So originally, back when ZFS was first introduced, we distributed writes across VDEVs just by how much free space they had. VDEVs that had more free space would get more writes. Ones that had less space would get fewer. And this, certainly works in terms of getting all the data onto disks, but it's not ideal for performance for a number of reasons. Um, more recent versions of ZFS, before version 2.4, used a different algorithm. What they did was, as they would give a little bit of work to every disk, and then as that work completed, they would give the disk more work. And so the idea basically was that faster disks would receive more data written to them, and this would give you maximum throughput to all of your different VDEVs. But this causes a problem if you have very unbalanced VDEVs, where one of them is almost completely full and one of them is mostly empty, or if you have very different devices. If you have a pool that's a mixture of solid state and spinning Rust, you could end up in a situation where some of the devices are receiving all the writes and some are receiving almost none, um, which fills up the faster devices very quickly, leaving only the slow device, um, which is problematic. And then also it affects future read performance because your data is concentrated on this one set of devices. Now, anytime you read it, all of the reads have to go to those devices, and the rest of your disks aren't helping as much as they could be because we didn't end up writing as much of the data there.
Yeah, so
So
especially after you add another set of disks, if they take the majority of the writes, because that's what makes sense, it means that when you read, almost all the reads have to come from there. So even once the VDEVs are balanced out over time, your reads are still going to be slower because that specific data is more biased to the one VDEV than the other.
right.
And so that's why we have the introduction of the unified allocation throttle, which tries to combine both approaches and use the best one when appropriate. So by default, it will try to fill VDEVs fairly evenly. So in this example, we have an SSD and a hard drive, and we're writing at less than the maximum performance of the system. So ZFS is writing, 125 megabytes a second to both the SSD and the hard drive here, trying to fill them up evenly. But in cases where we are actually trying to write as fast as possible, right? The system has more incoming writes than it has capacity for, then ZFS will do the second graph where it write more to the SSD in order to achieve the performance that you need. But over time, this will trail off. As the SSD gets more and more full and the hard drive proportionally is more empty, it will slow down the writes to the SSD and put more of it towards the hard drive. In this case, writing to the hard drive as fast as it possibly can the whole time, meaning that it won't allow the SSD to completely fill up too soon so that we still have the ability to burst and get that higher performance when we need it, but not waste it when we don't need it. And because of the way this works, it's actually improved the performance even if you don't have any SSDs. So in this example where they had 12 5-wide RAID Z1 VDEVs in a pool, before this unified allocation throttle, you could get about 3 gigabytes a second of 16K blocks, but now you can get 3.6 gigabytes a second. So a 17% improvement. And if you're using the default 128K record size, you can even get as much as a 23% improvement. So this is quite a big change. On the larger record sizes, you don't see as much of an improvement. That's because we're already kind of saturating the hard drive and we weren't limited by IOPS. But the newer allocation throttle does seem to do a much better job of kind of combining, keeping the devices even, but still using the fastest one when it makes a difference. And it's a very big performance win for a lot of workloads.
Yeah, so as Alan mentioned earlier, gang blocks are a feature in ZFS that is sort of the storage option of last resort. So if you're writing some data to ZFS, say you're using the default 128 kilobyte record size, um, when you write a 128 kilobyte block of data, we need 128 kilobyte free space on disk to put that data. Um, and if your pool has been around for a while and there have been lots of writes to it and it's been in operation for a long time, you can end up in a situation where there is enough free space in total to store your data, but there is no single chunk of space that's big enough. Throughout your entire disk, maybe there are no 128 kilobyte free chunks left, or if you're using a larger record size, it can happen even sooner. And so the way ZFS ensures that it will still be able to store your data is gang blocks. And the idea there is we split the data into smaller pieces. and then store those smaller pieces in whatever free segments we can find. Previously, all of the different gang members, these smaller pieces of data, had to be the same size, right? They would all have to be, 42 and a bit kilobytes in our example. And we would find, we would find these three 42 kilobyte regions and store the data in those, and then have a little header that points to that data. But if you had, for example, a bunch of 64 kilobyte free segments, using only 42 kilobytes of them to store these gang members is wasteful, and it's actually creating more fragmentation going forwards. And so in ZFS 2.4, gang member sizes are now dynamic. We will try to allocate sort of any amount of space that we can up to the size that we're trying to store, letting us use fewer gang leaves and creating less data fragmentation and less free space fragmentation going forwards.
Yeah, it's a very big improvement to not, make the situation worse when you're in this, when you don't have enough space. Breaking up the biggest spaces you have into even smaller spaces was really counterproductive.
Yeah. And there's actually some more changes that we made as part of this version. So I mentioned that gang blocks split the data into three pieces. And there's a reason for that. And the reason is that these gang headers that we use to track the children are always stored in a single sector on disk. But we kind of just assumed that regardless, no matter what the A shift actually is on your device, we would only ever use 512 bytes of space, which is enough to store three block pointers. So we could only have three gang children, regardless of what your sector size actually was. And so in cases where there's really serious fragmentation, where, for example, you couldn't even find a 42 kilobyte free segment for your gang children, you would actually have to gang the gang child. And so you end up with multi-level ganging, where you have a gang header pointing to gang children, which are themselves gang headers pointing to gang children, and so on, which is a huge performance problem, right? If you're trying to read this data on a spinning metal hard drive, every time you go down to a different layer, you have to do another set of seeks. If each seek takes a few milliseconds, this can add up to tens of milliseconds of additional latency to do a read. Um, And so the new feature that we added is that the gang headers themselves are now dynamic. They can now leverage whatever sector size your pool is using. So if you have 4 kilobyte sectors, you can store, I think, about 24 or 25 children, instead of just three at a single level, which significantly reduces the need to do multi-level ganging. It makes it much, much easier to fit everything in a single layer, which saves you a lot of latency, if you are being forced to resort to these gang blocks.
Yeah, saving those couple of seeks can make a big difference.
Yeah.
If each one's 5 milliseconds, it can really, and not only that, is it taking those milliseconds is using up the IOPS. And if you
Mhm.
are on a hard drive based pool, IOPS are very precious. You only have a couple hundred of them.
Yeah.
So if you'd like to know more about how ZFS works and especially how to operate it, Clara has the ZFS Basecamp, which is a centralized learning resource for everything about ZFS. So it covers everything from the very basics, like what is a VDEV you were just talking about, and covers, what do I need to know about ZFS to decide to use it? I'm deciding to use it. How do I build my first pool? Through, all right, I have a pool now. How do I maintain it? How do I back it up? And then finally into, I've been using ZFS for a while. How do I tune it and get the most out of it? All of that is covered in the Basecamp. We have articles, webinars like this, white papers, case studies, video snippets, everything you need to continue your journey learning about ZFS. Now we'll get into kind of a lightning round, cover some of the other changes to ZFS that, we don't need to spend quite as much time on. The first is the new default quota feature. A pain point we've heard from larger institutions, especially universities and so on, that are managing a lot of users is that having to set the quota for every user is kind of an administrative burden in itself, but also it means that if you want to change the quota for everyone, you also have to go and change it for every user. Whereas if you could just say, here's a default quota that applies to everyone, including new users, and then I can change a couple of specific users' quotas if I need. So ZFS now has the default quota feature where you can set what the quota should be for newly created users. And that means it's just automatically inherited and makes your life much easier when managing a large number of users. Next, we have topologies for special VDEVs. Before 2.4, if you were trying to use the special VDEVs, which stores just the metadata and optionally small blocks in ZFS, your only options were a stripe or a mirror. And we very, very strongly recommended mirrors because if you lose your special VDEV, then that's all the metadata for the pool. You can't find all your file data is there, but you don't know which file's which. And it would basically the pool would not work. And so your only option being mirrors got very inefficient if you needed a lot of metadata, right? If you're building a multi-petabyte pool and you needed tens of terabytes of metadata, doing that with mirrors got very expensive. And there was no specific reason it had to be that way. So we've modified the rules for special VDEVs so that you can use RAID Z on them as well. And then kind of related to that, if you have a small number of ZVols on your system, for example, a VM you run on a server, you can now opt that small blocks on a ZVol, which in general will be all the blocks because all the blocks on a ZVol are the same size, can be written to the special VDEV. So if your whole pool isn't made up of ZVols, where you would need all your storage to be special, it allows you to have those small blocks go to your metadata VDEV and provide that performance, which is a really nice way to have optimized performance for one or two important VMs, while either the rest of the VMs or the rest of your non-ZVols live on the hard drive based pool. You can have the SSD or NVMe based for the VMs that really need it.
Another feature that's new in ZFS 2.4 is related to the fast dedupe feature. Um, there are some the fast dedupe feature uses a log to store the dedupe updates rather than having to sort of do all these random accesses that the older version of dedupe used, which was already a big performance win. But there were some more changes to make to get it even better. And so we did some of that in this release as well. We increased the block size a little bit to make the compression better. Um, and we completed the process of sort of syncing out that log in just a single pass rather than doing it in lots of little steps to smooth things out and improve performance across sort of the sync process and bring down sync times. Um, it reduces lock contention and it gets better performance by about 10% on sort of just the process of syncing out this dedupe table data.
Yeah, there were two other small changes. The first was the block size of the dedupe table itself was increased from 4 kilobytes to 32 kilobytes. That means that the table itself can be compressed, which will save some disk space, but importantly means that when we're caching it in memory,
Mhm.
we're able to use the compressed copy and basically fit more DDT in the same amount of RAM.
Right.
And the other change was around hole compression. So in the past, only if you had compression turned on would ZFS notice a block was all zeros and write it as a whole instead of as a regular data block. But if you were using dedupe but didn't have compression on, it meant dedupe wouldn't notice that, and you would end up with, if you had a lot of holes in files like sparse files from VMs or thin provisioning, it would have the block that just happens to have the checksum of all zeros have a very, very high reference count. And it meant
Mhm.
ZFS was doing a lot of work to keep track of, oh, there are 100,001 copies of the block of all zeros. Whereas now it can actually detect, if you have dedupe on, but compression off, it will still do the check, be like, oh, is this block all zeros? If it is, write it as a whole, and we don't need to bother with dedupe for it. And that can be a very big optimization for that case.
Yeah.
There were a bunch of optimizations for BRT, the block cloning or ref links as well. Um, Again, kind of reducing the lock intention there, using more task queues when you're freeing blocks so that it can do the preemptive reads it needs to know if it needs to update the BRT table or to fetch those parts of the BRT table it needs to update. And similarly, we increased the block size from 4K to 8K so that we could be able to leverage some compression since the BRT blocks tend to be quite compressible. But we were more conservative with the 8K because we don't want to update you have too much write amplification when we're updating the BRT. And then lastly, a small Linux specific thing. In the later 6.x kernels in Linux, um, the Linux kernel changed how it deals with directory entries and inodes. It switched from kind of after you've closed the file and aren't using it anymore, it would tell ZFS, okay, I'm going to garbage collect this, and ZFS could free its memory related to those. But after the change, it kind of keeps them around unless there's memory pressure. And this resulted in ZFS having a lot of its memory locked down where it couldn't free it because it was in use by the Linux kernel, like the object was referenced. And so it made ZFS have a lot harder time managing its cache and not running the system out of memory. So now there's an option where you can enable to have ZFS instruct the Linux kernel to not try to keep those D entries and inodes around. And ZFS's cache will keep the data if it's frequently used so that we can easily recreate those inodes and D entries if you open the file again. But we're not, pinning down a lot of memory on something in the hopes that we might use it again later. Before we get to questions, we have a poll. We'd like just to get some short answers from everyone about how you heard about our webinar and how we got you to join us today. And then we'll get to some of the questions. Okay, so Charles asks, I'm still waiting on a way to be able to evacuate a VDEV even if that means I have to use the ZFS rewrite feature, so I can kick out a set of 4 VDEVs that are made up of 8 terabyte VDEVs. And he confirmed in the chat there that they are RAID Z VDEVs. So I think right now there's not anything on the roadmap that would let you evacuate RAID Z VDEVs. But maybe Paul, you can talk for just briefly about what any RAID might enable.
Yeah, so AnyRAID is a new VDEV type that we've been working on over the past year or so. Um, and one of the features that I'm working on right now actually is so AnyRAID lets you store data. Um, lets you create a single VDEV that uses mirror parity or RAID Z parity, but it lets you combine devices of different sizes, which is very useful for a lot of users. Um, and one of the other things that it lets you do is because of the AnyRAID architecture that we came up with, it actually lets you evacuate single devices from the AnyRAID VDEV and redistributes the data on them to other devices in the VDEV. So that's something that might be an option for the future when you're leveraging AnyRAID to store your data.
Yeah, the goal there is to add a lot more flexibility to how you manage the pool and have fewer situations where you're kind of stuck like Charles is right now.
Yeah.
So another question we had submitted from Cedric was, is ZFS encryption considered fully production ready, or are there still bugs in that area? I think with 2.4, we nailed that last kind of lingering bug.
Yeah, at least the last one that was sort of known to be causing issues. Um, I mean, it's software. You can never be 100% sure you've squashed all the bugs, but I think everything that we've come across has been resolved at this point.
Yeah, every known or often seen bug is definitely fixed now. So with 2.4, I think we're in a much better place for ZFS encryption in production.
Yep.
And we know quite a few people using it. So we have pretty good confidence that we're okay there. So next, Brian asks, with respect to recovery from ransomware or whatever, can you describe the steps involved in recovering a virtual machine data set from a snapshot after it was compromised or corrupted or whatever? So it depends how you set it up. If you basically have a backing file like a VMDK or a QCOW or a raw file or whatever in a data set, if you have snapshots of that, you can either what I would normally suggest is you clone the snapshot and rearrange things so that you run the VM out of the clone, and that way you'll have a good copy of the data from the time of the snapshot, but you keep the corrupted or compromised VM in case you still want to investigate it further, or if there might be individual files that didn't get encrypted yet or something that you want to pull out of that. For zvols, it's pretty much the same. You have a snapshot, you can either roll back and throw away all the changes, or clone it and have a second zvol that is the good copy from the snapshot. So there's not really a lot of procedure there. It's just either clone or roll back and use the last good copy. And the advantage with the clone is you keep the bad copy in case you want to investigate further or recover things. Next up, Carlos asks, I'd like to know if it's possible to extract metrics with tools like Prometheus Node Exporter, specifically on ZFS and things like capacities and snapshots. So yes, there is a ZFS Prometheus exporter that exports a lot of very rich detail, especially some of the internal metrics in ZFS. Although I don't know if it actually exports the capacity of the pool and like the remaining free space. But it definitely gives a lot of useful information about like how much memory ZFS is using and for what. The number of events, if ZFS had to go slow because we were short on memory or there was too much incoming data or various other things, it has all of those metrics. So yeah, Prometheus, there are a bunch of good node exporter stuff for ZFS. Some of them are also in the official GitHub repo under contrib if you're looking for some examples and so on. And then Paul Vixie asks about SSD considerations and roadmap. If I have a system that has 10 NVMe U.2 drives, how should I think about Z-pooling them? And will that answer change in the near or medium term? I don't know that it'll change that much. Your main choices here are mirrors versus RAID Z. Some of that will have to do if you're trying to get more IOPS, mirrors is probably better. And then a RAID Z will be better for throughput. On writes, especially on reads, it's kind of more of a toss-up which one will actually give you more read throughput. But if you're trying to write as fast as possible, the RAID Z is likely to give you that and has the main advantage of giving you more of your usable space. Did you have any other thoughts there, Paul?
I mean, in the medium term, any RAID will also be an option for future expandability and for flexibility with some of the stuff we've talked about. But if they're all the same size and there's not plans for, significant future expansion, sort of the existing options are going to do just fine.
Yeah. I think most of the changes that would come to improve NVMe wouldn't affect the choice of pool layout. It would just be improvements in ZFS to make
Yeah.
things faster.
Yeah. Most of those improvements are above the device layer and so are agnostic to the VDEV type.
Actually, jumping back for a second to Carlos's question about the Prometheus node exporter, Charles, who asked a previous question, points out that there's also the InfluxDB plugin for ZFS, which takes all those metrics and puts them in the InfluxDB time series database, which can be a very useful way to store those metrics. So that's another option in addition to Prometheus. Okay, I think we're almost out of time. Maybe we have one more question that maybe we'll sneak in. Doesn't look like. Okay. So thanks everyone for joining and definitely get in touch if you have any needs for ZFS. If you need support for your existing pools, if you need help designing your new pool, or if you want to look at the performance of a system and try to make it better. Clara has experience with organizations of all different sizes doing all kinds of different workloads, whether it's university storing research or home directories, or movie editing, media production, color correction, all kinds of different workloads. All right. Thank you.